Hello everyone. In this presentation, we will discuss what is parsing. And before going to discuss what is parsing, we will see what is parse tree. Then there are two types of derivation we have, that is your leftmost and rightmost derivation, and then ambiguity. What is ambiguity and how ambiguity can be removed? Okay, that is your unambiguous grammar. So myself, Dr. Mrinal Goswami, I am going to teach you all those concepts related to your parsing. So in this slide, we will see how high-level language is converted to a absolute code, or you can say executable code. So HLL, capital HLL means here it is your high-level language. That is a input of your preprocessor stage. That means preprocessor stage always take input from high level language and it is converted to your pure high level language. So question comes, what is pure high level language? Or you can ask me, what is the difference between high level language and pure high level language? Your high level language contains all those macro expansions and header files, but after pre-processing stage, those header files and macro expansions are removed from your high-level language code. That code is called pure high-level language. That means your pure high-level language doesn't contain all those macro expansions and studio.h file, or you can say that is your header files. Okay, but how without header file or macro expansions your code will be going to run? That is a question again. When I say that your pure high level language doesn't contain header files or macro expansion file, it doesn't mean that they don't have those informations. Actually, that studio.h file, in this case you can see, if preprocessor stage preprocessor stage directly paste it or directly write all those lines which is inside their header file. That means header file include studio.h header file is removed by inserting all those lines which is written inside that studio.h file. That is called your pure high level language. Now in the second phase, that pure high level language is going to feed to compiler phase. Now that compiler actually generated assembly level language, that is your platform dependent. It is known to us that assembly level languages are platform independent. That is your compiler output. Then again that assembly level language is given to a assembler, and assembler going to generate your object code, and you can say that is your machine code which is relocatable. Actually this object code or relocatable machine code is stored in hard drive. Okay, please remember that object code or machine code which is relocatable cannot be loaded into the main memory without linking and loading process done. That means with the help of linker and loader only, that machine code which is relocatable, or you can say that object code, can be converted to your absolute code and executable code. And now we know absolute code and executable code, those are pure machine level language, and that absolute code or executable code, that code can only run on your machine. Okay, so these are your phases of a compiler. Okay, there are 1 2 3 4 5 6 phases are there. First is your lexical analysis phase. So output of a lexical analysis phase is stream of tokens, and then that stream of tokens are going to feed to your syntax analysis page, and it will generate your parse tree. Our main concern in this presentation is your parse tree generation or parsing. So that means we will mainly focus on that syntax analysis phase. Okay, now that parse tree is fed to again your semantic analysis page, and it will generate parse tree which is semantically verified. And then that semantically verified parse tree is a input of intermediate code generation. Then it will generate, that means your intermediate code generation will gives you the three address code, and then those three address code are fed to a code optimization phase. The the main motive of the code optimization phase is to reduce the size of the code. That means unnecessary symbols, unnecessary codes are removed in this phase. Then in the target code generation, it is directly generated absolute code and executable code. And you can see symbol table and error handler is related to each and every phases of a compiler. Please remember, symbol table and error handler are related to each and every phases of a compiler. Now in this slide we will see how a high level language is converted to machine level language with the help of compiler. Already we have discussed that there are 6 pages of a compiler. Now we will see in detail. So in the lexical analyzer phase, high level languages are converted to stream of tokens with the help of regular expression, finite automata, and the symbol table. In the symbol table, we actually not we compiler store all the related information related to high level language. Okay, so finite automata comes into play in case of lexical analyzer, and it is converted your high level language to your stream of tokens. In this case, high level language is x equal to a plus b, then into c, that is converted to id equal to id plus id into id. That is, id means here that is your identifier. Now this stream of tokens are supplied to syntax analyzer phase, and then syntax analyzer phase with the help of some grammars, that is basically context free grammars, generate your parse tree. So main concern of this top lecture is parse tree, parsers. Okay, so in the syntax analyzer phase we can see the parse tree is generated with the help of some context free grammars. Then this parse tree is again fed to a semantic analyzer phase, and in this case semantic analyzer phase, that parse tree is again evaluated whether the parse tree is meaningful or not. That is why this is called semantically verified parse tree. After that, intermediate code generation, that is your ICG, generate tree address code of your parse tree. So please remember, lexical analyzer phase, syntax analyzer phase, and semantic analyzer, and then intermediate code generation. These 4 phases are called front end of a compiler, and code optimization and target code generation, these 2 phases are called back end of a compiler. In this slide we will discuss what is ambiguous grammar and how ambiguity can be removed. Now if I have a grammar e is equal to e plus e, then e is equal to e into e, or in the last e is equal to id in the same level. Okay, and now we need to generate this id plus id plus id string. Now using these productions we can form two different types of parse tree. These are called parse tree. and if we can generate more than one parse tree for the same input symbol, or you can say string, then that grammar is ambiguous. Here you can see we are generating the same input symbol. This is your id plus id plus id. Similarly, in this case also, id plus id plus id. We are generating the same input string or uh, input using the same grammar, but we can generate two different parse tree for the same input symbol. So basically, you can say the grammar is ambiguous. How we can define ambiguity? If we can generate more than one parse tree for the same input symbol, then we can declare that grammar is ambiguous. Now question comes, how can we remove that ambiguity from an ambiguous grammar? Now let's say I converted the above grammar into this form. This is my modified grammar now. And if I apply first production, that is your e equal to e plus id, then I can generate this e plus id. Now again, now what we are doing here, my intention is to generate the same input string id plus id plus id using the modified grammar. Now in this second production also I have applied the same production e plus id. In the third production I can replace e with id. Now you can see id plus id plus id. So you have your input string id plus id plus id using our modified grammar. Now if I wish to generate one more parse tree, can I generate one more parse tree here? No, because our modified grammar not permit us to generate more than one parse tree. So this grammar, we can declare that this grammar is unambiguous grammar, because using this grammar we can generate id plus id plus id, which is intended to generate, but only one parse tree is possible. So this type of grammars are called unambiguous grammar. So I think you people got now what is ambiguous grammar and unambiguous grammar. Ambiguous grammar always contain more than one parse tree, but in case of unambiguous grammar, we can generate only one parse tree using that given grammar. Now, in this example, you focus on this input string id plus id plus id. We know plus is an left associative operator, isn't it? So we know it, plus is an left associative operator, and if I apply any one of these two parse tree, in this case, because of this plus operator, your parse tree, both the parse tree will generate the correct output. But the main concern is we need to restrict the parser, or you can say your syntax analyzer, into only one parse tree. That is our motive, because we will always feed an unambiguous grammar to our parser. Okay, so in this second modified grammar, you can see the left associativity is preserved, but in this two grammar, the left hand side grammar is left associative, but the right hand side grammar parse tree is not left associative. But our modified grammar will generate always a left associative parse tree, because all the non-terminals are replaced in the left hand side only. Okay, so this type of parse tree or grammar, we can say left associative, as well as it can be declared that the grammar is also left recursive. Why left recursive? Because we are removing or replacing, or you can say calling, the same input again and again on the left hand side only, not in the right hand side. In the right hand side we are always generating terminal symbols. So this type of grammars are called left associative as well as left recursive grammar. Now uh, in the earlier grammar, that means earlier parse tree, these are the parse trees. Because of that plus operator, we don't get any uh, different output. Okay, if I use if I use this parse tree also, you will get the correct output. If I use this parse tree, right hand side parse tree also, you will get the correct output, because plus is an left to right associative operator, and in our input string everything is written in the form of plus operator. But if I use this type of input string id plus id into id, we know that the multiplicative operator should be performed first, because multiplication has higher precedence over your addition operation. So in this case, if I take this input, okay, and we have applied the same grammar, then I can generate again two more parse tree. That is why again we can say that the given grammar is ambiguous. Now in this case, if I apply or your parser use this production or parse tree, then then the output will be a wrong output, because in this case you can see the plus operation is performed first, then multiplication. So we need to remove this type of unambiguity from our this type of ambiguity from our grammar. And these are uh, this type of ambiguity are in the grammar because of precedence and levels are not declared, or you can say not formally written in the grammar. So in the above grammar, this grammar, you can see all the productions are in the same level. Also in the input symbol or input string, precedence are not taken account. Now if I remove, or you can say if I modified the grammar like this, in the first level, this is level 1. In the first level I have addition operation. In the second level I have multiplication operation. In the third level I have input string or terminal. So if I apply this grammar, I can generate always I can generate the multiplication first, then only addition, because the multiplication operation is on the level 2. That means if you put, or if you put your multiplication operation, that means higher precedence operator should be in the lower level or higher level. That means in this case, this level of multiplication is higher than the level of uh, addition operation. That is the requirement, because we know multiplication has higher precedence than addition, so it should be in the higher level, that means level 2 in this case. So if we apply this production or this grammar, we will able to generate always multiplication before addition. Take one more example. In this case, this is my grammar, and I have power of operator, multiplication, and then addition. And you can see here the power of operator has the highest precedence, then medium precedence of multiplication, and the uh, addition operation has the lowest precedence. Now you can see in this case the level 3, or I can say, yeah, level 3 contains this power of operator. This means the power of operator will be performed first, then multiplication, and then addition, because the levels of power of operator is the highest. It belongs to the highest level, and multiplication belongs to the medium level, and plus or addition operator belongs to the lowest level. And this is called precedence or level. So There are two types of concepts related in this slide. That is, one is associativity, another is precedence or label. So we always remove or restrict our grammar in one direction. That is, if we have left associativity, then we will perform left associative uh, operations or productions, and if you have precedence or levels, then we need to define, or we need to follow precedence rule. And how to follow precedence rule? Maintaining levels. If you placed your highest precedence level in the higher level, highest precedence operator in the higher level, then you will able to generate that operator first in your parse tree. Now in this slide we will see recursion. What is recursion? So in the earlier slide also, we have discussed left associativity and left recursion. So there are two types of recursion, basically left recursion and right recursion. Already we have discussed what is left recursion, but we will discuss again here in this slide. So I have a production, or you can say grammar, like this: a equal to a alpha, then I can generate a beta. So if I use this production a beta directly, then this is my minimal production. You can say this is my beta is my minimal terminal symbol. Okay, now if I apply a alpha, then I can generate this type of parse tree. And you can see here also, input a or non-terminal a is replaced in the left side only. In the right side we have our terminal values. So using these two production, I can write formally beta alpha star. This is my generalized output, because in this second parse tree you can see beta alpha alpha. That means I can generate alpha as many times of I require. Okay, so if I place epsilon in this alpha, that means this alpha will be finished here, and this is my minimal terminal string. So this type of productions, or this type of operations, or this type of parse trees are called left recursive parse tree, because in the left side only we are replacing our non-terminals. Okay, and if I follow this type of production, okay, then you can generate same alpha, a to beta, and this a alpha beta production. If I use this production, first production, then I am able to generate all the non-terminals in the right hand side, and this is the generalized output of this grammar: a alpha a, then beta. That means in the left hand side we will able to generate alpha star and beta in the right hand side. And this grammar is left recursive, because every time we will need to replace my non-terminals on the right hand side of the parse tree. Okay, so left right recursion, there are no harm using no, there are no harm if you use right recursion, but left recursion is a harmful effect, because left recursion can generate infinite loop. Left recursion can generate infinite loop. If I apply this type of code, then it may happen that because of this a function, it will goes into an infinite loop, and that is why we don't require and don't use left recursive grammars. Always we prefer right recursive grammars. And one more important point to note here: your top down parser, one of your top down parser, there are many types of top down parser, one of the top down parser cannot parse left recursive grammar. Now question comes, how to remove left recursion from a given grammar. If we consider the earlier example, if I consider the earlier example, or you can say earlier grammar, that is your a equal to a alpha then beta, then we can able to generate This is my uh, generalized output alpha beta star. Okay, now if I want to remove this left recursion, this is my left recursion because my input symbols are on the left hand side only. So if I want to remove left recursion, I need to do some modification on my productions, or you can say grammar. So if I replace this grammar with this, then I can say the left recursion is finished from the modified grammar. How? If I write a equal to beta alpha, but we are following this. Okay, please remember we are following the output of the grammar. In place of beta I can put beta, but in place of alpha star I have a dash. Now it is the responsibility of a dash to generate the rest of the production. So you can see the a dash generating epsilon, because if I put epsilon in this place I can generate the minimal string, that is your beta. And in the place of alpha star, if I put alpha a star a dash, then I can able to generate your alpha beta star. So this is completely same with this earlier grammar, because we are generating the same output which is generated by the previous grammar. But in this case you can visualize there is no left recursion. See, this is your beta, here it is alpha epsilon, and in this case also the a dash is present in the right hand side. That is why this you can say that this is left this is right recursive grammar, but this is not in left recursive grammar. So we are interested to remove left recursion from the given grammar. So take an example. In this case I have e equal to e plus t and then t. Okay, now you can see clearly e is in the left hand side, so this is your left recursive grammar. Now we are interested to remove the left recursion from the given grammar. So how to write left recurse how to write the modified grammar? So let's take e equal to as a, this is your a, then a equal to, this is actually I am following, this is the original grammar. So this is my original grammar. Now we are converting the original grammar into our modified grammar. So compare these two grammar, a a a a, then plus t is your alpha here. Okay, then beta is your t. Now write in the form of modified grammar. E is equal to e plus e is equal to t in t into e dash. Why t here? Because the first production of the first symbol of this modified grammar is beta. So in this case I have t, then a dash. A dash means e dash, and then e dash generating epsilon, and then alpha. What is alpha here? Plus t. Plus t is your alpha, then a dash. A dash means e dash. Got it? So now we will see one more example. Let's take this third example. You can do your second example at your home. So in the third example, you can see in the first production we don't have any left recursion. Okay, this is my start symbol, this is L. So S and L both are not same. You can say there is no left recursion. But in the second production you can see here also I have L, here also I have L, and L is present in the left hand side. So we can declare this is a left recursive production or grammar. Okay, now compare this production with this. What is A here? A is your L. What is A again in this case? A is equal L, and then alpha is your comma S. This is your alpha, and beta is your S. So using again this production, modified productions, I can write L equal to S, which is your beta, then L dash, and L dash alpha is comma S, then L dash, and then I can write epsilon here. So using this modified grammar, we can remove left recursion from our given grammar. So now we will discuss left factoring. Okay, but before going to discuss left factoring, I am interested to discuss some points here. So I have three types of grammar basically. First is ambiguous grammar or non-ambiguous grammar or unambiguous grammar. So we don't require or we don't prefer ambiguous grammar. Always we prefer unambiguous grammar. Okay, then left factoring. In the previous slide we have seen left factoring has some harmful effect, that is your infinite loop. So we always prefer right recursive grammar. Now here D represents deterministic and ND represents non-deterministic grammar. So in this type of grammar we always prefer deterministic version of our grammar. We don't prefer non-determinism or non-deterministic grammar. So you can recall your finite automata, that is your NFA, that is a non-deterministic finite automata, where you can see the non-determinism. Here also we have the same concept. Let's say I have a grammar A equal to alpha beta 1, then alpha beta 2, then alpha beta 3. For the same input symbol, I have three choices: first choice, second choice, and the third choice. That is why this is called non-deterministic. Okay, this is your non-determinism, because for the same input symbol A I can have three choices. I can go to this production, I can go to this production, I can go to this production also. Okay, now I am interested to generate alpha beta 3. I am interested to generate alpha beta 3, but I can see this is my third production, but your parser cannot directly see the third production, because parser, or you can say your syntax analyzer, don't have that power to visualize or to see the third production first, because we always, or your parser always scan the input symbol from left to right, from left to right. So it will scan this input symbol first and it can see alpha. So it will go to the production and see A equal to alpha beta 1. So the parser thought that, it thinks that the first symbol is alpha. Here also I have alpha, so I can proceed to using this production. But after scanning the second input symbol only, the parser will know that this is not my correct output, because I need beta 3 here and I am able to generate here beta 1. So I need to backtrack. That parser will backtrack to the first production or your start production. Okay, similarly in this second production also same thing will happen. So it needs backtracking, but after generating the third production only, it will able to generate the required output. So this type of backtracking is happen because of the common prefixes, because in the same in the output and input we have some common prefixes, that is your alpha. In all the productions we have common in alpha, and also in your input symbol, that is expected output symbol, is also having some common prefixes. So this type of common prefixes always generate backtracking. So we need to remove common prefixes as well as non-determinism. There is a concept called left factoring, through which we can remove the non-determinism. Okay, this is my original grammar, and if I want to generate non-deterministic version of that grammar, then I can write like this: A equal to alpha A star. Then it is the responsibility of A dash to generate the rest of the productions. Here I can write beta 1, beta 2, and beta 3. Then in this case you can see I can directly able to generate alpha beta 3, because the first production will always produce you alpha A dash. Now it is in this A dash symbol, you can see nothing is common in the right hand side. it is beta 1, beta 2, then beta 3. So I can, or not you can, actually your parser can able to generate directly beta 3. So left factoring always remove non-determinism as well as common prefixes from your grammar. Now, in this slide, we will see different types of parsers. Already we have discussed three different types of grammars. Why we have discussed grammar before reading or before studying parser? Because parser always takes that grammars, okay, that syntax analyzer phase. You can see in the second third slide we have discussed the details of all the phases of a compiler, where you can see in the syntax analysis phase we have something called grammar, because to generate the parse tree or correct parse tree we need grammars. So before discussing parser, we need the concept of grammar, how ambiguity can be removed, why left recursion is harmful, why we always prefer right recursion, why we require deterministic grammar. Okay, now in this slide we will discuss the classification of parsers. Here you can see parsers always found in syntax analysis page. So there are two types of parser basically. One is top down or predictive parser, or another kind of parser is your bottom up or shift reduce parser. Again, we can divide top down parser or predictive parser into two phases. One is recursive descent, where we have full backtracking, and another is non-recursive descent, where we don't have any backtracking. And also this type of parser, non-recursive descent parser, is also called LL1 parser. In the right hand side we have bottom up or shift reduce parser. It is also of two types. First is LR and second is operator precedence parser. And in the case of LR parser, we have four another classification, that is your LR0, SLR1, LALR1, CLR1. Now, already we have discussed we don't prefer ambiguous grammar. Always we need unambiguous grammar. But in this case, you please remember the operator precedence parser can handle ambiguity. This is the exception. The operator precedence parser can perform your ambiguous grammar. That means it can handle ambiguity. None of the parser except operator precedence parser can handle ambiguity. So please remember, operator precedence parser can handle ambiguous grammar, but rest cannot handle anything. That means always need unambiguous grammar except for operator precedence parser. Now I have written here leftmost derivation. That is why, because top-down parsers are always generate with the help of leftmost derivation, and bottom-up parsers are always generated with the help of reverse of rightmost derivation. We will discuss leftmost derivation and rightmost derivation, or you can say reverse of rightmost derivation, in the next slide. But here focus on the other concepts. And one important concept of non-recursive descent parser, or you can say LL1 parser, is it cannot handle left recursion and non-determinism. Always it needs right recursive grammar or deterministic grammar or unambiguous grammar. Unambiguous grammar, it is common for all, but non-recursive descent parser cannot handle left recursion and non-determinism. Please remember. Now see here, LL means, what is LL? LL means it will scan, that means your parser will scan from left to right, and it is always used leftmost derivation. And what is LR here? It is in short form. The full form is left to right for the first L, and the second R represents reverse of rightmost derivation. Reverse of rightmost derivation. Now we have SLR, LALR and CLR. SLR, the full form of SLR is simple LR. LALR, the full form of LALR is look ahead LR, and the third CLR represents canonical LR. The power of all these LR parsers are written here. That means you can see LR0 has the lowest priority or power, and canonical LR has the highest priority and precedence in this LR parsers. Now we will see here how to produce leftmost derivation and rightmost derivation. So we know the top-down parser use always uses leftmost derivation, and bottom-up parser always uses reverse of rightmost derivation. Please remember, not rightmost derivation. Bottom-up parser always uses reverse of rightmost derivation. Let's say I have a grammar S equal to AABE, A equal to ABC, then B, then B to D. Now I am interested to generate A, B, B, C, D, E. If I use this grammar, and I can generate parse tree like this. This is my top-down parser. I start with the production S, then I have replaced the A here, then in the same level I have replaced the D here, and then third level I have replaced A again here. So you can see I have the same leftmost derivation for the parse tree here. You can see these are all the productions or non-terminals are replaced from the left hand side. First I have replaced A here with the help of A, B, C. Then I have replaced B here, A here with the production B. Then in the last line I have replaced capital B with the production D. So you can see everything has been done in the leftmost side, and that is why this is called leftmost derivation. I think you people know what is leftmost derivation. And similarly in the bottom of parser uses the reverse of rightmost derivation. So you people know, I think, rightmost derivation. So we apply reverse of rightmost derivation in the bottom up parser.